So we're going to try and get you through a little bit of an understanding some of the foundations of inequalities and where do inequalities show up in our world. And then I want to show you a couple of examples of where it doesn't really work out. There's some really crazy things that can happen, and I'll give you those examples here as well. So let's go ahead and get started. When we talk about intro to inequalities, we're talking about these symbols: the less than symbol, less than or equal symbol, more than or equal. Oftentimes we talk about greater than or equal to. And the example that I gave the other day is amusement park rides. So in this case, the little kiddo needs to be 42 inches or smaller. So we could say student, kiddo, whatever the variable, the height has to be smaller than or equal to 42 inches. But I have a little video here that explains why, for safety reasons. It's not just for no reason at all. There really are some legitimate reasons why they have 42 or 48 or 72 inches. And let me get you through that here. Through a commercial first.
As parks are beginning to reopen after the coronavirus, a few have changed the way that height is measured, with a few opting to allow family members to measure their own child's height rather than a trained ride operator. Accordingly, it's now more important than ever for the public to understand height requirements and why they're in place. In most cases, height requirements are set by the ride's manufacturer and are normally based on the smallest body size the ride's restraints can safely restrain. This means that trying to sneak a child onto a ride that is under that ride's height requirement could result in that child being ejected from the ride due to the ride's restraints not being able to hold them into the ride. This is especially possible if the ride experiences an unusual situation. On some older 48-inch rides like Gemini and Magnum at Cedar Point, trains can sometimes stack, and when this occurs, they will stop very suddenly in the brakes. In this situation, riders who are too short can be thrown from the ride's restraints. This is the reason that many seemingly tame rides have very strict height requirements. Vekoma, in their manual for the Boomerang model of roller coaster that is installed at many parks across the globe, states that passengers should be at least 1.20 meters in height to prevent the danger of sliding out of the shoulder.
So here's an example of where it says at least 1.2 meters. So at least would mean bigger than or equal to. It's got to be 1.2 meters, which is about 37 or 38 inches. But it's got to be equal to that or bigger than that.
Restraint. This is roughly 47.2 inches. But many U.S. parks have their boomerangs listed as 48-inch or taller attractions. This is where we get into height requirements set by parks. In the case of the boomerang, the 48-inch rides are at this height simply because it's much easier to tell guests and enforce a height of 48 inches instead of 47.2 inches. But sometimes parks may change height requirements from what the manufacturer recommends due to them feeling that due to the way the ride is operated, it's not safe for younger or smaller guests. Six Flags Darien Lake, for example, has a Vekoma boomerang that requires riders to be 54 inches tall to ride alone, but allows 48-inch tall riders to ride as long as they ride with an adult. This is because their primary concern is that a 48-inch tall rider can squeeze through the restraint and try to exit the ride while it is in motion. Another example is RMC's hybrid coasters, which can accommodate a 48-inch tall rider, but rides like Steel Vengeance and Cedar Point have a height requirement of 52 inches. This was due to park officials riding Steel Vengeance and feeling that due to the high amount of negative G's the ride pulled combined with the long ride experience, the ride was not suitable for riders under 52 inches. Some rides also have a maximum height requirement. This is often around 78 inches and is normally in place so that taller riders do not hit their feet on something during the ride.
So a maximum height of 72 would have to say you have to be 72 inches or smaller than that in order for it to work. So less than or greater than is like smaller than or bigger than. So in this case, you saw if their rides are, if you're too tall, you're going to end up dragging.
Tricks like stuffing a kid's shoes or giving them extra long hair is the oldest trick in the book, and ride operators are trained on how to notice this. For example, height is always measured off the top of the head, not hair. And if ride operators suspect that a child is wearing height-enhancing shoes, they can ask for the child to remove them so they can get a more accurate measurement of their height.
So that kind of gives you, there's a little bit more of the video, but we don't need to go into it. It gives you just a practical example of where less than or equal to shows up. So let me now move into a couple little facts or ideas, foundational elements about inequalities. This first idea talks about the difference between having an equal sign and not having an equal sign. When I see x's that are smaller than 5, I could get really close. I could say like 4.99999999999999999, and that gets pretty close to 5, but it says you can't equal 5. So we show that we get really close but don't equal it. We include it. We show that by having a circle that's hollow at that endpoint. We don't include when there's no equal sign. But when this says it can be equal to or smaller than 5, the extra little mark here tells me I have to do the extra little step of including 5, and I show that by filling in the mark. The same is true if we go in the reverse direction. Numbers that are bigger than 5, numbers that are bigger than equal to 5 would have to have that filled in. So what I really want to do is talk to you about the fact that for years and years it's been more beneficial for students to get rid of that idea that I have to read from left to right, greater than or less than. I think it makes more sense if I get you used to reading from the variable away towards the number. This is saying things that are smaller than 5. We already showed what that looks like. But this is also saying, even though you would read it 5 is bigger than x's, I think it makes sense. These two things are saying the same thing. If you read it from the x, the smaller end of the symbols towards the x here too. X's are numbers that are smaller than 5 is the same as x's that are smaller than the 5. X is smaller than 5, x is smaller than 5. Doesn't matter which way we're going as long as you start from the variable and work towards the number. This is the answer that works for both of those statements. So I've got 3 quick examples, but before I do that, I think I need to explain there is this little trick about flipping symbols around. And if I just give you an example, I think Ms. Hyde did a really good job of showing the mathematics of why it works, but here's an example of when it works that makes sense. Talking about money, if I tell you I have $86 and you have $57, in other words, I have more than you do, I could show that with the symbol. The larger end of the symbol is towards the larger number. But if I want to talk about owing money, maybe the way I can represent that is to multiply this by -1, multiply this by -1, so that the numbers are negative numbers. And if I just bring this symbol straight down, up here it works because on a number line, 86 is further to the right than 57. The larger numbers are always to the right. But when I multiply by a negative, those two numbers, 86 and 57, are actually flipping to the other side of the 0, and 86 now is farther to the left. When I flip, I have to remember that I have to flip this symbol around in order for us to maintain a true statement. So when you multiply by a negative or divide by a negative, you've got to remember that this thing flips around in its orientation in order for us to maintain true statements. So here are the 3 examples. Pretty straightforward set of problems. It incorporates 2 different things that are worth talking about. The first is if I just have a statement here, this looks like an equation. It's got the equal sign replaced with the symbol is all, but we're going to go through the 3 steps that we used last week. Can we simplify the left or right? No. Does it have variables on the left and right? No. So step number 3 says isolate the x by moving the numbers one at a time to the other side of the inequality. So if I subtract 3 from both sides, the 3's here will cancel. -5 minus 3 more puts me further in the hole at -8. So here's another statement that means the same thing as this. It's just a little simpler. And now to get x completely by itself, to isolate it further, I'm going to divide by -2. And when I divide by that negative, that's why I put it here. I got to remember, I put it in red right here to remind you, you've got to flip the symbol around. -8 divided by -2 is a +4. So we're saying numbers that are bigger than 4. Notice I have this here because I want to have you check this. If you leave the answer like this, I think people are going to be able to find that the endpoint is 4. But which way to go? You can always wrap up a problem by checking. You're saying 0 should work, and if I stick 0 in here, I'd end up with -5 is bigger than 0 plus 3, and that's not true. This statement back here, again, if I'm reading from the x towards the number, we're looking for numbers that are bigger than 4. So really the more appropriate way of, the more accurate way of showing this answer is going to look like this. Numbers that are bigger than 4. I should be able to stick any number out here like 100 in. I could stick 100 in for the original equation. -2 times 100 is -200. Plus 3 is -197. That's really far out on the left-hand side. -5 is further to the right on a number line, so -5 is bigger than -197. So when I stick in 100, which we're saying is one of the numbers that should work, it does work, and I'm feeling better about that problem. So I got two more colorful situations. These aren't as complicated, but they bring up an interesting point here. Actually, I think I've got 3 quick examples to go through. Same kind of problem, but I want to show you sometimes you're going to end up with 0 as an answer, and that's okay. We're looking for moving the 3 to the other side. We're going to add 3 to both sides in that case. But I'm seeing that the answer is not 0 here. The answer is actually 1, which is kind of interesting. When I divide both sides by -2, I've got to flip that symbol around, so there's all sorts of nutty mess stuff going on with this thing. This should be flipped around, and let me just highlight when I flip, I'm going to include it being yellow, just as a reminder. But when I divide both sides by -2, I end up with 1. So I think that this is the right answer algebraically. The number line should be, we're looking for numbers that are bigger than 1. This is completely wrong. This should be flipped around. The only thing that seems to be right about it is that it's hollow, but I think it's going to have to be at 1. Numbers that are bigger than 1. And again, I should be able to test that. Anything bigger than 1 I should be able to put in here and it'll make it a true statement, like 10. -2 times 10 is -20, minus 3 more is -23. And sure enough, -5 is bigger than -23, so that number did work. I should also be able to stick in a number that doesn't work and see that it doesn't work. If I stick in 0 here, I end up with 0 minus 3 is -3. -5 is not bigger than -3. It's further to the left on a number line. So we didn't want 0 to work. It didn't work, so I'm feeling comfortable. This just should be at 1. So that's the kind of thinking that you got to go through to work these problems. Here's the, oh my goodness, what happens here? When I look at this, the first part of any problem says simplify, so I'm going to distribute here to get rid of the parentheses. Second step says, do I have variables on both sides? And in this case I do. When I subtract 2 x's from both sides, something weird happens. When I subtract 2 x's, the x's disappear completely. And I'm left with a statement that says 12 is bigger than -3. And in fact, I think on a number line, 12 is to the right of -3, so 12 is bigger than 3. When there are no x's, what we're saying is that originally the left-hand side is bigger than the right-hand side regardless of what we stick in for x. This is going to be x plus 12. This is going to be x minus 3. Anything with 12 added to it is going to be bigger than anything with 3 subtracted from it. So any number that you use, when there's no variables left and the statement is true, the answer is that all numbers work. And then the final example. If I come in here and just let me fix this real quick. So in this particular problem, it looks similar to the other. I just changed this from being a plus to a minus. When I distribute, step number 1 says simplify the left or simplify the right. Distribute gets me into a simplified look for the left-hand side. 2 times x and 2 times -3 or 2 times 3 with a minus sign. We've distributed. To go from here to the next step, I'm going to subtract 2 x's again. And this is similar to the last example. When I subtract the 2x from both sides, the x's disappear. There is no more variable. The issue that makes this unique from the other problem is that -6 is left and -3 is left. We're saying -6 is bigger than -3, and on a number line it's further to the left. This is not a true statement. So when you have no variables left and it's a false statement, the answer is there's no red line here. There is no number that we could stick in for the original x. The left will always be smaller than the right. It'll never be bigger than, which is what the symbol here is asking us to begin with. So the answer is that there is no answer here. So that's it. You're going to have some problems to just practice with a little bit here today. Tomorrow you'll have a little bit more in detailed practice. We're going to try and get you into groups and work together. But today we've kind of laid it out. You just have to kind of work through 10 problems. We don't even have you show a whole lot of work. You'll just see if you're on the right path. Until tomorrow, stay happy and stay healthy.